So let's ask the famous question, which is here, coastline paradox. Okay, coastline paradox asks, what is the length of the coastline of Great Britain? Okay, you can ask the same thing for Turkey, doesn't matter. So the paradox lies in the following. How do you measure it? If you use big sticks, you get some number, right? If you use smaller sticks, you get some other number. If you let an ant walk around Turkey and find the number of steps it took, you get some other number. So which one of them is the correct one, right? So from here, actually, I hope you pronounce it Benoit, or something like this, Mandelbrot, got interested in this question, and he came up with the thing that we nowadays call fractals, right? The objects that are self-similar to themselves. So let me show you a typical example of a fractal. Just wait for a moment. Okay. So for example, let's take a triangle. Each side has length 1. Okay. So what is the total length? 3. Very good. So now I add something like this. What is the total length of this part? Any ideas? 4. Very good. Because you had like 3 over here, like, yeah, it's 4. It is 4. So you went from 3 to 4. What about if I add yet another bump over here? Now? You went from 3 to 4, right? Now you will go from 4 to 4 times 4 over 3. Okay? If you add this one, and I promise I will not draw the whole thing, then you go from 4 times 4 over 3 times 4 over 3, right? Where do you reach if you go to infinity? Yeah, infinity, right? Because it keeps increasing. But do you leave this surface, this boundary? No, you don't leave that boundary. So now we have a dilemma, right? We have, do you remember I mentioned this before? So we have a curve that never meets itself, right? But it is also confined in a, I mean, it could be something like this, that never meets itself, and it is not confined. But we know that it is confined, but it is an infinite line. So its dimension is actually between 1D and 2D. Okay? It's not a one-dimensional object. It's something else, right? And there are many ways to describe this dimension. One of them is to look at the following. So we are basically going from a straight line to this one, right? And then we are going from this one to this one. So what happens to the scale? So you can see that this one is similar to this one. You only take this one and plug it in. So the scaling is 3, right? You scale it by three times. But how many copies do you use? 1, 2, 3, 4. So one of the ways to define this dimension that is between 1 and 2 is to write down ln 4 divided by ln 3. How many copies you used, how many scaling you needed. And this gives you some value. And this is not the only way to define this dimension. Another way is to draw a map. So for example, if you didn't have this kind of weird object, but instead if you had something like this, okay, what would happen? You would still get more and more distance, right? So one way of approaching this is the size of the ruler. Do you understand what I mean by this? And this is the length of the system. But you draw this in log scale. Log of this one, log of this one. And you will get a line. So remember, if we calculated Britain coastline with large distances, then we got something that is less than what we get when you do it precisely, right? So you will get some values that are like this, and that's the slope of this is another way to determine the dimension. Are you with me? Yes? Okay, so let's actually look at, after this part we will just have fun with fractals, okay? So one of the famous fractals is Mandelbrot set, which can be, let's go to YouTube. Mandelbrot zoom. Have you ever watched one of these? Yeah, remember I mentioned this one in the first lecture, right? And I promised that I will derive it for you. I will write the program of this one for you. So you can see that this is an object that if you zoom in, the complexity never ends. And actually it's an object that has itself in it many times, right? This one is a particularly beautiful zoom, but let's just, of course, to get this kind of beautiful zooms, you need to write the program properly, long program probably. But let's write a short one and a simple one, okay? So first I need to explain you how the Mandelbrot fractal, how do you get it, right? So it's very easy actually. So let's say you choose a point in a complex plane, okay? Let's say this point is C equals A plus I times B. So this is A, this is B, okay? Then you start with Z equals 0. Z is a complex number. Then you do Z squared, Z new, you can see that here we have also mapping, right? Zn squared plus c. Okay. So what will be the new Zn? Like Z0 is 0. What is Z1? C, right? A plus IB. But finding Z2 is much more complicated, right? So what it has to do with Mandelbrot set? Basically, Mandelbrot set is the set of points that do not diverge if you take this to infinity. Do you understand? So, no? If you keep doing this, let's do it for some value. For example, let's do it for -1. Okay, z equals 0, c equals -1. Okay, so what is the next z? Z1 is z2 is -1. Very good. What is z3? Yes, -1 squared plus -1, 0. What is z4? -1. So does it diverge? No. Then -1 is inside Mandelbrot set. Okay, is one of its members. Okay, and you do it for all points, and if you only plot the ones that stay without diverging, then you get the Mandelbrot set. Okay, so let's look for Mandelbrot program. Yes, this one. You can see that it is not that complicated. So let's start with a mesh grid between -2 and 2. Okay, so I'm basically taking a square of points between -2 and 2 in x-axis and y-axis. Okay, then I define c at each point. At each point, the c is the x-coordinate plus I times the y-coordinate. So c is a complex number at each point. Then I define z. Okay, let's say define c at each point. Okay. Now I define z to be z is 0 initially at every point. Are you with me? Yes? So what will be the next value of z? You basically take the squares at each point, you add c, you get the new z. Okay? That's it. And what I'm going to draw is the absolute value of z between 0 and 2. Why between 0 and 2? Because if the absolute value of z is more than 2, then for sure this will diverge. Okay, because I know that. Okay. Can I draw it now? So you start with this. If you keep doing it, remember that to get the actual Mandelbrot set, we need to do it for infinite times in principle, right? And the more you do it, the more these fine structures will appear. Okay? Let's actually zoom somewhere over here, and how I will zoom? Not by doing this one. Okay. Wow. Yeah, today is any questions while MATLAB restarts? Did you understand Mandelbrot set? And but we don't know why it has this weird shape, right? I will come to that in a moment. Let's do it again. So this is the Mandelbrot set, and let it happen for a while. Then we stop this, and if you zoom, you will see like these structures, right? But they are not well formed because we didn't go to infinity. Let's look at a particular region, a square from 0.2 to 0.6, but making it finer. You will see one of the edges, okay? You will see how it appears. So you can see that it is related to the length of the coastline of Britain or whatever, right? The finer you get, the longer it becomes. Okay, I want to start with a game. It's usually called chaos game. And there are various kinds of it. I will mention one of them. So think of 3 points, A, B, and C, and the corners of an equilateral triangle. Okay? Then take any point in space, like this one. Okay? So now what you do is you pick up a random number between 1 and 3. Okay? Let's actually rename it to 1, 2, 3. So if you pick 1, you go from the point you are currently on to the midway of U and the point 1. Do you understand? If you pick 3, you go over here. If you pick 2, you go over here. Any questions so far? No questions. Okay, let's see if we code this, what happens, okay? So I will do it this many times, okay? And I'm pick n random numbers between 1 and 3. Do you have any problem over here? We did it before. No problem. Then these are coordinates of 3 points. Coordinates of 3 points. You see 0, 0, 1, 0, 1 over 2 square root 3 over 2, which will give you 3 points on the equilateral triangle, right? Then here I start with, basically I make all the points 0, but more importantly start at 0, 0. But you can start anywhere you want, okay? Then what this one does is the next point is determined by what I've just mentioned. The coordinate of the point determined randomly, do you see? Nth random point plus current coordinate divided by 2, right? Go midway between points chosen at random. Okay, then I plot it, right? So let me start with 1,000 points. Okay, I don't want to give away the surprise. It already gives away the surprise. Anyways, so if I take it to 1,000,000 points, or is it 100,000? You get this beautiful picture. If you go to million, it just takes a little bit more time, but you get this fractal, right? So let's look inside this one. You can see that it has itself in it infinite times, right? So first let's understand why this is happening. Okay, let's try to understand this. So basically, if I start with all the points over here, okay, let's just all the points, and if I apply the first rule, where all these points are mapped, like this one will map here, this one here, they will all be mapped over here. Do you agree? If I choose this point, if I chose this point, they will all be mapped here. If I chose this one over here. So this is basically very similar to the von Koch curve that we described before, right? I said before. Interesting. Do you remember this one? It also involved similarity, right? Do you remember, do you have any questions so far? Yes. The rule is that if you are at any point, let's say if you are at any point, and you choose one of the corners at random, okay, either 1, 2, or 3. If you choose 2, then you go midway between the current point and the coordinate of 2, which is going over here. So what I just did is to take all the points possible, okay, and to apply all the rules, okay, at the same instant. Then I go from this one to this one, right? And if I apply this one more time, then I basically will map the whole thing into this triangle, and this triangle, which will give me something like this. Do you see? And keep repeating this, and you will get this Sierpinski triangle. Okay? So we mentioned similarity dimension. Do you remember similarity dimension? Do you remember this? What was it? How did we find the dimension of this one when it goes to infinity? So we had m copies, and the thing was scaled by n. So ln n, log or ln m divided by ln n would give you the dimension, right? What was m? How many copies do we have here? When I go from, say, this one to this one. Yes, I have 4 copies. M is 4. I have how much this one is increased? Like this one goes here, so 3. ln 4 over ln 3, right? There are many other definitions of dimensions, fractal dimensions. But first, let's find the similarity dimension of this one. And I promise we will come back to chaotic attractors and we will tie all this thing up today, okay? Hopefully. So what is the similarity dimension of this one? How many copies do you have? 3. So 3 copies. What about the scaling? Look, this one, if you multiply it by 2, I mean multiply sides by 2, and you will get the big one, right? So n is 2. So the fractal dimension is around this one.
So when we think about the n, we only think in one dimension, not like area.
Yes, exactly. Thank you very much. So it's about the scale in 1D, yes. But fractals can be not self-similar, right? There are fractals that are not self-similar. For example, I don't want to give an example, doesn't matter. For example, Lorentz map is not necessarily self-similar, right? Do you have small Lorentz maps inside Lorentz map? No, you don't, right? How will you find the dimension? So there are many other dimensions, and one of the rigorous ones is Hausdorff dimension, and I will not tell you what it is. Instead, I will talk about pointwise and correlation dimension. I hope I'm saying it correctly. Yes. So what it means? It means that, for example, if you have a 3D object, okay, take any part of the 3D object, take any point. So I will talk about pointwise first. If you take a circle around it with a radius r, okay, how do you expect the number of points engulfed by that sphere to go? It will be proportional to r cubed. Do you agree?
Circle or sphere?
Sphere, sorry. 3D, sphere, yes, a ball. So then it means that if you are plotting it log n versus log r, what do you get? A slope of 3, right? Yes, the slope is 3. Everybody agrees? So we start from here, and now this is pointwise dimension, and you can totally understand it for 3D objects. But if you have something complicated like a fractal, you would like to average it out, and you would like to do it for all points, right? And then average it out, right? So that's what we are going to do. That will give you the correlation dimension, okay? So basically, what you will do in the case of correlation dimension, you will choose a point, okay, and let's say there is a vector c, okay. You will choose different values of r, like, and I will use exponential, like, so e to the minus 5, e to the minus 4, e to the minus 3. This is the values of r. So I will not just go like, let's see what happens with 1, 2, 3, but I will go in the log scale, okay? So how many points do I have on the average when I have this much uh, radius of balls, etc., okay? And then if you plot it for a weird shape like a fractal, okay, then you will get something like this: log r versus log c gives you something like this. Okay, so it will be linear only in a certain range, but it will be linear there, and that will correspond to its dimension. Why do we fail here? Because our object has finite bigness. Finite size. Thank you. And why do we fail here? Because we have finite precision. Okay? In between, it's perfectly linear, almost perfectly linear. So let's do it for Sierpinski triangle first. Are you with me? Do you have any questions? No? So here it is. And let me start with this one. So let's say this is the radii of circles. In this case, I will just use circles, because even if I used 3D spheres, it would be the same answer, right? So I will choose circles that will start with e to the minus 10 and e to the minus 9, e to the minus 8. I will choose, look at each one of them. Then I have this C that has size of D. Basically, if I run this one, what do I get? So this will be my different measurements, right? How much points do I engulf when I use this radius, when I use this one, when I use this one, when I use... Is it clear to everyone? Yes. So then I have to count the numbers that are engulfed. So basically, let n be the number of points. Okay, this is the number of total number of points. This is number of points that were selected at random to average C. Do you understand? So I will choose not like 1,000 points on the Sierpinski triangle, 1,000 different points, and for each one of them, I will calculate how many points I'm engulfing with each one of them, and then average them out. I will divide by 1,000. Does it make sense to everyone? Yes? Good. This is where you find number of points engulfed or enclosed, maybe. Finally, I divide by NC, which is okay. Are you ready?
So we just check the distance with the radius, right? We compare it between the point and the center of that circle.
Mm-hmm.
If it's greater than the radius, then it's outside the circle. If it's less, it's
Yes.
inside the circle.
Yes, exactly. This one is doing that one, that thing. So for every point, it checks. Maybe this line is a little bit complicated. Basically, let's think about this one. So this one will subtract every x value from the x value that we have chosen, right? And take the square of it. Then this one will do the same for y coordinates. It will calculate the squares, right? So you will have a vector of distance squared, and it will compare each one with the distance that you have chosen. If it's smaller, then it will count it. So it will count the sum of all points that have this condition. Okay, let's run it. Well, did I choose? Yes, okay. So we have chosen too many points, I guess. But anyways, do you see this one? Yes? As we expected, right? So now you can see that in this region, you don't see it, but from -4 to -3, it is quite linear, right? So let's actually concentrate on that particular region. So I will comment it out and do precise calculation. So I will go from -4 to -3 now with not 1 by 1, but with 0.1 steps. Okay, are you with me? Yes? So I'm doing it. Yes, I have a line. Do you see a line? Very well. Let's do fitting. Let's fit it to a line. And what do you get? 1.58 something, right? What was our similarity dimension? It was ln, no, log corresponds to ln, right, in MATLAB. Log 2. So you get perfect result from both analysis. Do you understand my point? Yes? Sometimes they do correspond to each other, sometimes they don't. Okay? In this particular case, I believe it does because it's a nice self-similar structure. There is a symmetry and all the niceties you want. Okay, very good. I wanted to briefly show you another chaos game, but let's not go too deep into this one. It's just beautiful, that's the point. So in this case, it's an engineered game that produces, wait for it, this one. Okay, tell me.
Normally, for example, if we just consider the one-dimensional, two-dimensional, and three-dimensional objects, for example, in that case, log m over log n, for example, if we increase the one-dimensional parameter 2 times,
Yes.
It goes to the square of the dimension. So if that's why it's like two-dimensional, and if it's like
yes, exactly.
So in this case, but wouldn't area again be the same in the sense that, like, do we have that analogy with this? So if we increase one side 2 times, it
yes.
will be like the 1.58 times of the
area. Exactly.
But isn't the area same? Isn't it again a two-dimensional object?
No, it isn't. That's the interesting. That's very interesting. So let's try to understand your question. So you are saying if I have an object that has this much, this is your object, right? If you take it to 2a, right? Like a goes to 2a, then area goes to 4a, right? So it is basically the side times to the power of square. So what about this one with all its oddities, right? Basically,
instead of areas, we think like how many copies you create, same thing?
Yes, I think so. Yes, exactly. Thank you for saving me. Yes, instead of area, let's think your way. How many copies did you create, right? Because area is ill-defined here. It's a bunch of points at the end of the day. And I'm not sure if it has finite area or not. It actually has 0 area. Do you understand my point? Does everyone understand my point? No? So this one has an area, right? But this one, as you put holes in it, at each time you put a hole, so when I put one of the holes, it goes from area A to 3/4A, I believe. Yes? Because it had 4 parts and I removed one of them. Then I do it again, and it has again, the area is diminished. At the end of the day, you are left with no area at all. So you have to have to use the copies concept. Okay. All this started with Cantor. So I really recommend you to read his work and how he showed using all this stuff and tying all this weirdness together. Yeah, he shows, for example, that some infinities are bigger than others. Have you ever heard of that? It is that person.
Is it copies of the dimension, one dimension below its size defining dimension? I mean, like, for example, the square is a 2-dimensional thing. So we look one dimension small. When we consider a 3D object,
yes,
we look one dimension smaller, we draw a circle around it. So I think it's like we always go one dimension below to check
I think, I respectfully disagree. Actually, you when you were talking about the scale, you are scaling in all dimensions possible.
I didn't really understand the copies thing. So, for example, in the squares that you just drew, isn't it still 4 copies? Like,
yes, it's 4 copies. In the case of square, you go to 4 copies, and it makes sense because you went from you increase the scale with 2, right? And you have 4 copies, and it makes sense because 2 to the dimension will be 4 and dimension will be 2.
yes.
But here you go to you increase it by 2 to the d actually equals to 3. That's why you get ln 2 times d equals ln 3. Okay, let's talk about it more. So how about this picture? I will just show you that something like this is possible in a computer. Okay, you can find much more details about this one typing Barnsley's fern. Okay, and I have also prepared this one, which starts with random points between 0 and 1, okay, a square. Then each time you do this transformation, just to see how this shape, just to see the dynamics of this shape. Basically, remember in the triangle we took it to 3 different places, those points. Now we take it to 4 different places, and each time we squish it different way. So let's do the first one. The first iteration would take these points to these weird places. Some of these rectangles are actually flipped. Okay, so let's do it again, and again, and again, and again. Do you see the fern appearing behind your eyes? So basically, at the end of the day, it's a structure that after the mapping maps onto itself, right? You can analyze this one as much as you want at home. Let me show you the dimension of the Lorentz attractor. Do you remember our Lorentz attractor? Let's actually run this. Yes, let's run this. And remember what Lorentz was. And while it will plot, it couldn't handle this.
Maybe the function you.
Yes. Yes, brilliant. Thank you. Thank you so very much. So I will just comment it out, the place where I calculate the dimension. So we all do remember this weird object, right? So can you have a guess what its fractal dimension should be? 1.5. Other guesses? 2.5? 1.5? Can we settle on 2? It's almost flat, right? So let's actually calculate its dimension using the same trick. So basically we will calculate the path, right? And then take these different measures here. Okay, this time I go from -6 to 12 for some reason. Let's actually do this. Okay, we already have calculated the attractor, so let's do this one. Do you see the same plot appears? The one that starts with, maybe I should put some makeup on it. Marker size 15. Okay. Do you see? So it has this region where we don't have enough precision to look here. We have to calculate a lot of trajectories with a tiny bit of dt to show that this still goes linear over here too. Okay. And over here we have nothing to do because the attractor is bounded, right? So what matters is this one. For example, going from 0 to 1 or 1 to 2. 0 to 1 is good enough, I guess. Yes, I've tried that one. So I will go from 0 to 1 with higher precision. Let's start from the beginning. So any questions? No questions? So I will do fitting now. Basic fitting, linear, and it's 2.05. That's exactly the number that the book gives us, by the way. 2.05. So it's almost two-dimensional, but it has a little bit of those merging surfaces, right? Do you remember those surfaces that were merging? That pops it up to 3 dimensions, but just a little bit. Okay? Do you have any questions so far? Yes.
So what we calculate is called something like fractal size, right?
Fractal dimension,
Fractal
yes.
dimension.
Yes.
So as far as I know, we call something fractal when it involves self-similarity patterns inside. But so how is it valid for the Lorentz attractor to calculate such a dimension? I don't understand that part because it's just some jiggly wiggly lines.
Okay, that's the. Yeah.
I think what you said first was wrong. Like, it shouldn't be self-similar. As long as the dimension is not a number like 1, 2, 3, it's a fractal. Because like it's like fraction, fractal. So as long as it's like 1.5, 1.3, it doesn't have to be like, because the England's
Coastline.
England's coastline is also a fractal, and it's not self-similar in the sense that like a triangle.
Okay, let me show you what I skipped, and I believe this will be a good answer to your question. So your question is, if I don't have self-similarity, how I can have self-similarity without having self-similarity, right? So one example is this one. So for example, if I take a solid two-dimensional object and apply this operation, okay, I remove the middle part. I no, I didn't make my point yet. Okay, just imagine that I remove all the middle parts, and it will be a self-similar object, right?
But it's not self-similar.
It no, it is self-similar. I didn't make my point, believe me. So this one is self-similar to this one, right? But what if I do the following? I start with this one, then I remove any one of these 9 places. So the second one is like this. Okay? So the third one is, I already removed this part, but from these parts, I remove whichever one I want. So I remove this one, for example. You don't, I can't draw it properly. So the point is that when you scale, just imagine a stock market, okay? Can you say a difference between when you put it to 1 month and to 1 day? Can you, if I remove the axis, can you tell me whether it's a monthly jiggling or daily?
I cannot.
No one can, right? Because it is self-similar in a different way. It has the same complexity. Did you get the answer? Thank you. Okay, so I wanted to talk about one more thing. Do you remember this paper? I was going to talk about this one, which has this creation of branchy stuff. Okay, so let me quickly tell you what is happening here. Okay, so this is a model that models diffusion limited aggregation. So there is an aggregation, but it is limited with diffusion. Like, okay, let me tell you the model and you will instantly understand what it means. So the model starts with a seed at center, okay? Then there is a point that starts from the boundary, and it does a random walk, okay? Do you know what random walk is? It's a random walk. So basically, let's say each time you choose a number between 1 and 4, okay, and you go according to those numbers, you go up, down, left, or right, okay. So this will appear something like this: Brownian motion. Do you agree? Yes. Everybody with yes? Tell me. Ah, and I thought that it. Okay. Thank you very much. So this is the seed. Okay. This is the new particle. Let's call it new particle. And this is the domain in which we are interested. So if the part you start with at the boundary of that domain, and you do this random walk, okay? If you stay inside, you stay inside. If you go outside, you start from a new point, because otherwise you could go over here and you have to wait for it to come back. Instead of waiting for it to come back, you start with a new point. And let's say eventually this one comes at a distance 1 to this seed. Like it could be to its left, right, up or down. Then it itself becomes a seed. Do you understand my point? Yes? Then you keep repeating this process, and you get another seed, and another seed, another seed, another seed. And eventually you have this branchy stuff. Do you understand my point? If you look at this picture, probably one of this one was a seed. Maybe this one, it looks big. Then they kept adding and they got this beautiful image. Do you see? Yes? So I happen to have a code for this one too. I've tried many different versions. So instead of explaining this one, I will just run it because we are running out of time. So let me first run it like this. Do you see the other point making these random walks? And okay, this one happens to stay inside. So yes, but this is just to show you what the code is doing, okay? Come on. Okay. Let me make it faster. So do you understand the point? By the way, since once you have some seed accumulated, each time you have to compare the position of the new point with all the positions of the seeds, right? So instead what I'm doing is I'm making this safe region where I'm sure that the seeds are, and I'm updating that region according to the growth. And I also have this buffer layer, etc., etc. You can analyze the code and you will understand it, I'm sure. But let's, instead of drawing each one of this movement, let's draw just the seeds as they grow. Do you understand? So this is much faster. Do you see them appear? Everyone? Yes? So I happen to have run it for longer time. And do you know how to save something? Like you go here, you click you right click on it, and you save as something. Okay. So I run it for a long time, and I've saved it as seed2, I believe, and I will show you the correlation with it. One moment. Yes. So let's plot this one. Are you with me still? Yes. This is what I got. Do you see? Do you like it? So how about this one? What is the fractal dimension of this one? I can take guesses now. 1.05. Nice one. Other guesses? Well, let's do first this one. You do understand what this one means, right? Already. Yes, you have this, again, this structure. Okay, so I will go from 2.5 apparently to 3, as I did before. So over here. It's wiggly, but it's okay. Let's do the fitting. Comes out 1.66, right? 1.66. It's almost two-dimensional. What about the paper? The paper talks about this minus 0.34, which is a different way of looking at dimensions. Normally, you have to add 2, the 2 dimensions. So 2 minus 0.34, what do you get? 1.66. So I think this paper introduces yet another way of looking at fractal dimensions, and they call it density correlation function, etc. So do you have any questions? Do we now understand the geometry of nature? Yes. Yes.
I only have a question about in programming how we are seeing this log and overlog.
In programming, you mean? Like in
how we measure the similarity constant.
like how we do the fitting?
Yeah.
The fitting? Only the
fitting. How can we have that graph similarity dimension?
Okay. So you only want to understand this one conceptually, right? This one, the log R versus log C. Why it has this shape? Oh, sorry.
Both that and how we take this in program.
So what we do in the program is we take the values of R equals to e to the minus 10, e to the minus 9, e to the minus 8, etc. Okay? And if you do logarithm of that, so log of e to the minus 10 will give you minus 10, right? So for minus 10 over here, you will count the number of points enclosed by that radius. Okay? The average number of points enclosed. Then you increase it to r to the minus, let's say e to the minus 5, which will correspond to minus 5 over here. And you will find the number of points enclosed, which is c, but you will take the logarithm of it. That's what we are doing. So this d, do you see, exponential minus 4 to 8, for example. So you take all the values in between.
So how are we not getting minus?
E to the minus 10 is, we don't have minus, you mean like in the plot? Like in the x-axis, we have minus.
No. If we log c is positive value, log e to the minus 1 is a negative value.
Yes, we have negative value, like minus 4, minus 2, 0, 2, 4, 6. Do you see? Let's stop here.